inference to improve performance and reason about its behavior statically while maintaining the probabilistic programming paradigm. So let's start with a motivating example. Here we have a radar tracking problem where we want to estimate the distance and altitude of an aircraft as it's flying using radar measurements. And how can we do this? Well, one method is to use Bayesian inference on a probabilistic model, and one tool that makes it easy to express probabilistic models is probabilistic programs. So that's right one for our situation. So first, since we want to model the distance and altitude, we instantiate random variables drawn from probability distributions. For example, here we have the variable x representing the distance being drawn from a Gaussian distribution, and its mean is the previous distance value. Here we write that as x0. And the variance is another random variable q, which is itself drawn from an inverse gamma distribution. Since we want to know the values of x and alt, we return that as the final expression in a tuple. Next, we want to condition our probabilistic model on radar measurements in order to actually perform the inference. And this conditioning is done with the observe keyword. So the first argument is the distribution of the random variable that we want to condition. Here, the first observe assumes the distance measurement is drawn from a Gaussian distribution centered around the true distance, and its variance is the random variable r, which represents the white noise inherent in radar measurements. The second argument of the observe keyword is the value that we want to condition the observed random variable to be. So in our program, those are the free variables x_ops and a_ops, which represent the actual data itself, which are also the inputs to the program. Lastly, when the aircraft is flying at low altitudes, when it's like close to the ground, the aircraft experiences additional noise modeled with the variable other. The if expression branches on the altitude value to use the sum of r and other when in low altitudes and just r otherwise. So altogether, we've created a probabilistic program that encodes this diagrammed probabilistic model for our problem, where the yellow nodes are the latent variables and the white nodes are the observed variables. And the program should output the distributions of x, which is the distance, and alt, the altitude, of the airplane as it's conditioned on the input data, which are x_ops and a_ops. So now the question is, how do we actually execute this program to achieve this? Ideally, we like to get an exact answer. So using exact inference to symbolically compute for the closed form solution would do this. But these type of algorithms can only solve problems that have nice properties, such as linear Gaussians or conjugate distributions that actually have analytical solutions. And in this case, in our program, there are no analytical solutions that we know of. So what can we do now? Well, we can use approximate inference instead. An example of how this type of algorithm runs is, first you would have multiple executions of the program, which is called particles. We execute the program in parallel, sampling each random variables as they are encountered. And conditioning is performed by weighing the particles based on the likelihood of the observed data. Here we indicate that by the sizes of the boxes. And the final solution is the weighted sum of the particles. This will get us an approximate answer to the inference solution. And these methods are great because they can solve all types of problems. The caveat is that the solutions can have high error with limited execution time. And resampling a new set of particles based on the weights at certain checkpoints can help lower the error in the solution. This type of approximate inference is called particle filtering. However, depending on the program, this still might not be enough to lower the error. So a third type of inference seeks to further address this, and they're called hybrid inference. So hybrid inference combines the flexibility of approximate inference with the accuracy of exact inference. And how this is achieved at a high level is the algorithm analytically solves parts of the problems and samples random variables when it can't make any more progress symbolically. For example, in this program, the algorithm determines that the variable q doesn't actually need to be sampled, so it keeps it as a symbolic expression. For the purpose of this presentation, we don't need to go into the exact details of how the algorithm makes this decision, just that it does some computation to figure this out. Putting it all together, a hybrid particle filtering algorithm would do the same thing on a bunch of particles and perform particle filtering the same as before, except some of the variables are kept as symbolic expressions. And in the end, we still get a solution, and the solution generally has reduced error. There's several of these hybrid particle filtering techniques for probabilistic programming languages, such as semi-symbolic inference, delayed sampling, and sequential Monte Carlo with belief propagation. However, there's a particular detail to hybrid particle filtering I'd like to point out, which is that there can actually be multiple different choices of random variables to be kept symbolic or sampled. We call each of these an inference plan. Here we have two different plans for our example program, one where X is kept symbolic and one where R is kept symbolic. Different inference plans can produce different inference accuracy for the same runtime. Here we have the error of the estimated distance across 100 time steps for each of these plans while given the same runtime constraint. So we can see that the symbolic X plan is slightly more accurate. However, different inference plans can also make different variables more accurate. Here, symbolic R is more accurate for the altitude. And choosing which representation to use then depends on, one, the probabilistic model, and two, the problem constraints imposed and the metrics used by the developer to evaluate the program. And hybrid inference algorithms use heuristics to decide which inference plan to use. And while these heuristics do take into consideration the probabilistic model given, because that's the program itself, they are oblivious to the developer's problem specifications, so they might select inefficient representations. Additionally, there might not even be a plan that achieves the best performance across the board, such as in our example. So even more so in cases like this, developers need an interface to choose an inference plan to achieve better performance based on their system considerations. So I will now present such an interface. So our interface is composed of two parts. One, the distribution encoding annotations that enable developers to express representation choices of random variables. The second part is satisfiability analysis, which I will get into later. First, I'll present the annotations. So we want to tell the inference algorithm in our program to keep R symbolic here. So what we do is annotate each random variable with either symbolic or sample to specify the representation of the variable that we want. So here, R is annotated with symbolic, and everything else is annotated with sample. When a random variable is annotated with sample, the program runtime will sample the random variable upon instantiation to satisfy the annotation. Here, the sample annotation causes Q to be sampled and collapse to a constant value. And this goes for all the other sample annotated variables except for R, which is annotated with the symbolic annotation. The symbolic annotation asserts that the random variable must not be sampled during the execution. It's an assertion, not an action. And sometimes this assertion can be false. So in our program, in some executions, the algorithm doesn't know how to perform inference without sampling R. So this means that the symbolic annotation is just unsatisfiable. And in this case, what the program can do is it can abort midway, or it can issue a warning and sample the annotated variable anyways to force the execution to continue. This means that the program is deviating from the annotations, but at least the program will continue running and produce a result. The trade-off of this approach is that the program is now implementing a different inference plan, which can have performance implications. So what that can look like is, for example, in our program, when the aircraft is flying at high altitudes, the annotations are satisfiable in both the symbolic X plan and the symbolic R plan, which gives us the error plots that we saw earlier. But in a different flight mode, when the aircraft is descending, the symbolic R plan has an unsatisfiable annotation because the input data is in a different regime. So now we see a much different performance result compared to the last slide. Specifically, the symbolic R plan has a significant error spike in the distance compared to the symbolic X plan. And this is beyond what's acceptable for our problem constraints. So as a developer, we wouldn't want to use the symbolic R plan. The bottom line is, to correctly reason about and choose inference plans, developers should know which plans do not ever have unsatisfiable annotations and which plans might in some executions. And so to help developers do this reasoning, we also developed the inference plan satisfiability analysis, which statically infers whether a given set of annotations are satisfiable for all possible executions of the program. The analysis is an abstract interpretation with an abstract domain over the symbolic expressions used by the algorithm. This allows the analysis to approximate how the algorithm makes decisions about whether to sample random variables. So let's take a look at the program that we've been looking at with the symbolic R plan annotations, which we know have unsatisfiable annotations in some executions. So first, the annotation notes that R is a symbolic random variable, whereas other is a constant value because we know that it's sampled. Then in the if expression, R plus other is noted as just the sum of R symbolic variable and a constant. Because R is symbolic, the summation itself is also a symbolic expression. The else branch is just the variable R. But to summarize the two branches, the analysis would infer that this V is some generic expression that references R. And finally, the analysis notes that the program is conditioned on a Gaussian distribution with these symbolic expressions as parameters. And the analysis will use these abstract expressions to decide whether the symbolic computations that is required to keep R symbolic can always be performed. And in this case, they cannot. So the analysis would return unsatisfiable as the judgment, which is what we want. On the other hand, with the symbolic X-plan in this program, the analysis recognizes that the mean of the conditioned Gaussian distribution is just the symbolic variable X, and the variance is just a constant. So it also recognizes that the algorithm can always perform the required symbolic computations that allow X to remain symbolic. So the plan is judged satisfiable. So that's the annotations in the analysis. And we also developed Siren, a programming language that implements the various hybrid particle filtering algorithms and supports the inference plans using the annotations and the analysis. So that's our interface. Additionally, we performed an empirical evaluation to answer two questions. First, does using inference plans offer better runtime and accuracy? What we're really asking with this question is there some set of annotations that can improve performance from the default behavior of these algorithms? So using 3 different hybrid particle filtering algorithms, we evaluated every satisfiable inference plan for each benchmark on the basis of runtime speedup and accuracy against the default. To summarize the result, for each benchmark and algorithm, we computed the geometric mean of the speedup across variables. So if there is a bar, that means there is an alternative plan that is faster than the default behavior. So as we can see, for all 3 algorithms, alternative inference plans are often faster than the default. Overall, it provides 1.76 times speedup on average. In terms of accuracy, we did something similar. We computed the accuracy ratio achieved by the best performing plan to the default plan for each variable. Then to summarize, we computed the geometric mean across the variables for each benchmark and algorithm. And as before, we can see that the custom inference plans also improve accuracy for a given runtime constraint. Overall, it achieves 1.83 times better accuracy. For a detailed breakdown of the performance result comparison, please see our paper. But to answer our question, yes, inference plans do offer better runtime and accuracy. And the second question we want to ask is the satisfiability analysis precise in practice? So we ran the analysis on a suite of benchmarks. For each benchmark and algorithm, we counted the total number of satisfiable inference plans and the number of satisfiable plans that were identified by the analysis. So overall, we found that the analysis perfectly identified all the satisfiable plans in 27 out of the 33 settings. And in 32 out of the 33, it achieves at least 75% accuracy. So overall, it's pretty precise in most cases, with a few exceptions where in tree and wheels, the joining of expressions just made them too imprecise for the analysis to definitively say that a variable annotated with symbolic will never be sampled. Another source of imprecision is from aliasing, which we observed in SLDS. Lastly, in SLAM, we saw imprecision due to widening we had to perform to ensure the analysis does reach a fixed point. Rather than that, the analysis was precise in practice. And so to conclude, to wrap up, using inference plans, programmers can optimize a program for better inference performance while maintaining the probabilistic programming paradigm through our simple annotations and our static analysis. They don't have to write their own inference procedures, and they don't need to maintain a deep understanding of the hybrid inference algorithm they're using. So in our work, we focused on hybrid particle filtering. However, the need to optimize programs for better performance exists for other types of algorithms as well, and so does the need for a similar interface to inference plans in those cases. Please take a look at our paper for more details, and that's it for my talk. Happy to take questions.
Great, thank you. Any questions? Oh,
just a very quick question, because quite get the inference showing what is satisfiable or not. What is the exact guarantee that it says? Is it guaranteed that if it says satisfiable, then it really is?
Yes.
Okay, thank you.
Thanks for the great talk. So a lot of these algorithms without annotations sort of are optimistic. They try to make something symbolic until maybe it can't be. And I'm wondering if you thought about, having a third annotation that says, like, let the system decide, try to be symbolic if it can. If it can't, too bad, prefer the ones that I annotated as symbolic. And what do you think that the system, either the implementation or the static analysis could be extended to handle that kind of annotation?
So what we currently do is that if you just don't annotate it, then the system will just decide and referencing what it has already. But it doesn't go out of its way to make the existing annotations work.
Great. Thank you.
Any other questions?
In the evaluation where you showed the speed up and accuracy improvement, how did you decide which analysis plan to pick? I mean, how did you decide which variables to annotate? Did you try a bunch? Is that the best over all of the options?
Yeah, so what we did was we did a enumerative annotation. We just did symbolic and sample for every instance that is like drawn from a probability distribution. And then we found the ones that were actually satisfiable. Like if it's not satisfiable, we didn't run a performance evaluation on it.
Practice, what is the workflow you imagine that a developer would use? Because like a priori, I don't know which ones to make symbolic or not. So what do you like? What is a good strategy?
So we generally assume that there's some heuristics that you do know as someone who's writing this model. So you would try some annotations, and you run the analysis, and it would just eliminate the ones that don't work. So you could do the same thing as I did doing the evaluation, where you have a script that enumerates all of them, and then eliminate the one that don't work, and then based on your own like evaluations and metrics to pick which one makes the most sense.
All right, I think we have time for one more question, if there's anything. If not, let's... sorry.
So your analysis checks whether it's satisfiable for, for all possible, with probability 1. But in your example, there were regimes where it was very low probability of breaking into sampling. So how do you expect developers to think about, like, if the analysis fails, should I still try running this anyway? And do you think there are relaxations of the analysis that could be useful?
There's definitely different designs to inference plans than ours, for sure. But I think the main point is that even if it's low probability, you might still want to know. And I assume that when you're writing this program, you have some kind of intuition of how likely this is. Like for our case, like the example program was, your plane's got to descend at some point, right? So.
Great, let's thank Ellie again.